We will now demonstrate a problem in descriptive statistics, actually two problems. So let's get straight to the data. So here's question one. Question one basically deals with data types. Classify each of the following as nominal, ordinal, interval, or ratio data. So let's just do a quick revision. Nominal data is categorical data that has no ordering or preference. So for example, simply describing the colors of trousers, blue, green, black, yellow. There's really no ordering in this case. If we talk about the colors of cars, we could talk about yellow, blue, green, white, black. There's no ordering. Ordinal data, however, is categorical data that has an order to it. So if we talk about grades, such as A, B, C, D, E, those are categories, but there is also an ordering of those values. A is better than a B, B is better than a C, C is better than D, and D is better than F. So there is an ordering of these categories, and as such we would refer to that as ordinal data. Interval data would be data that is quantitative in nature. We have equal intervals between values, and however, there is not an absolute zero. So we talked about temperature, for example. 0 degrees Celsius doesn't mean that temperature does not exist. It simply means that it's a reference. Okay, and the ratios don't necessarily make sense, such as 40 degrees is not twice as hot as 20 degrees. We're not sure about that. So what we have done is that we have taken a scale and graduated that scale using equal intervals and allow us to classify temperatures along that scale. Ratio data, on the other hand, the data is numerical data or quantitative data, but the ratios make sense. And there is an absolute zero. So if we talk about distance, if we say 0 meters, then there's no distance. If we say 2 meters and 4 meters, 4 meters is twice as long as 2 meters. So that makes sense. Okay? So let's look at the first one. The amount of money a family of 4 spent on food each month. So if you think about it, that's quantitative. And is there an absolute zero? Yes, there is, because if you think about $0 spent, that means that you spent nothing. If you spent $100 in one month and $300 in another month, then you spent 3 times more than the first month. So in this case, this would be an example of ratio data. Okay. Ranking of 4 cars. Now notice ranking. Right away we should recognize that there is ordering here. Ranking of 4 cars in a safety test after they have been designed as excellent, good, satisfactory, and poor. So these are categories, but these categories have some ordering. Of course, excellent is better than good, good is better than satisfactory, and satisfactory is better than poor. So in this case, that would be ordinal data. That would be ordinal in nature. Time required to install 4 tires on an auto assembly line. So time is quantitative. If there is an absolute zero, zero time means it doesn't exist. 1 hour versus 2 hours, the ratio makes sense because 2 hours is twice as long, and so therefore that is ratio data. Number of years each employee worked for the company. Again, number of years, 0 years, 4 years, 12 years, etc. We know that's ratio. Dollar value of sales, again, that is ratio data. Telephone area code, well, in that case, that's categories. You could look at it as categories. So if you think of a city or you think of a country, 902, 416, 514, 506. So these are basically categories. There's no ordering, so that's just nominal data. Your Visa card numbers, again, no ordering, so that's nominal. And then annual student enrollment, well, that's quantitative, and there is an absolute zero. Zero enrollment means that no students enroll. 400 versus 800, the ratio makes sense, twice as much, so that's ratio. So as you could see, we really don't have any interval examples in this case right here. One of the ways to get interval data is that if we took a scale, a rating scale, and then we converted it to numerical values. So for example, if we took excellent, satisfactory, etc., and we said, let's make excellent 10. Let's make some good 5. Let's make fair 0. Let's make poor -5, and let's make very poor -10. So there is a 0 point there, a reference point, but it's not an absolute 0. And the -5 is not half as bad as a -10, or 10 is not twice as good as a 5. All right, so, but that would be an example of converting a ordinal scale to an interval scale by changing the categories and giving them and assigning them numerical values. Let's do another example that looks at measures of central tendency. So in this case, we want to look at measures such as mean, median, mode, standard deviation, variance, coefficient of variation, etc. Okay, so let's take a look at this question. Gail Pooley, the marketing director of Southeast Insurance, has been worried about the increasing age of the company's policyholders. She wants to determine whether the new advertising campaign has had the desired effect of attracting a large number of younger customers. As a first step, she has selected 2 samples of customers. The first sample is selected from the customer base before the new advertising campaign. The data are the age of the customers at the time the policy went into the effect. The second sample is taken from the customers who were added after the new advertising campaign. So we see we have 2 data sets, and if we count, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically 20 in each of them. All right. So the sample sizes, so these are samples, it's not obviously not a population. N is equal to 20 in both of these cases here. I think they're equal. And we've been fortunate that we've been given the sum of the x's, sum of the x squared, sum of the y squared. We call them x and y just to differentiate between the two. But we didn't have to. We could, if we're dealing with each of these samples independently, we could still use x as the variable. So let's go to the analysis on these questions. So the first question is to calculate the mean, median, and mode for the 2 samples. And this is a good example because it allows us to do comparison between those 2 samples to determine whether or not there's some differences. Now, just a quick reminder that mean is x bar, and x bar is just the sum of x over n. That's fairly straightforward. The median is a position value, and the way in which we calculate the median, if you may recall, is that we use the median is x n plus 1 over 2. That is the n plus 1 over 2 is the location of the median, and if it is if our sample size is an even number, then we have to go in between the 2 middle numbers. If it is an odd number, then we pick that middle number. So that's the median. And then, of course, we know mode, by definition, is the most frequent value. All right? So that is the mode, the most frequent value that occurred in the distribution. So the first thing that we should do when we are attempting to calculate things such as the median, because these are position values, is that we ought to order the numbers. So if we start before and we took the data, we have to order them, and it's useful to just order it in ascending order. So I'm going to just show you. We have 20 values. So if we go before, we have values 1, 2, 3, up to 20. I'm not going to do all of them. Here we go. So this doesn't look all that good. Let me just erase this slightly. So the first value, the smallest value to the largest value, in terms of before, would be 25. The youngest person is 25. The oldest person is 64. All right? And if we will look at some others, so this was 29, and then this is 30. And you could check out the rest of the distribution for yourself. And that's before. If we go after, then we have the values are 23, and then we have 24, 25, and the highest value is 44. So maybe just looking at these two sets on the surface, it might seem that after the campaign may have already worked, because the range is from 23 to 44, whereas before it was 25 to 64. That's what it seems like. So let's find the mean of before. X bar before is equal to the sum of x over n, as you recall, sum of x over n, in which case the sum of x is equal to 885, so 885 divided by 20, and that gives us a value of 44.25. X bar after is the same thing, sum of x over n, which is equal to 641 over 20, and that gives us an average age of 3205. All right? Of course, our units years. So that's the calculation of the mean. That's fairly straightforward. Let's look at the median. So if we want to do median, the median, if we recall, is x n plus 1 over 2. But what is n plus 1? So n plus 1 over 2 is 20 plus 1 over 2, which gives us 10.5. So the median, the location of the median is x 10.5. That's the location. That means that if we look at the ordered values, here, location 1, location 2, location 3, up to location 20, then we're looking for 10.5 somewhere in here. Well, what would happen is that we would have 10 and 11, so 10.5 would be this value in the center. So how do we get that? Well, if that value does not exist, we should really be averaging the 10th and 11th values, right? I'm going to just shrink that a little bit, move that over to the corner, and let's do that. So in the case of, I didn't show all of the values in the distribution, but in the case of before, x before, the median, sorry, not x before, but the median before is, so if we look at the 10th and 11th values from the data set, the 10th value is 42, so x10 plus x11 over 2. It turns out that that is 42 and 44 over 2, which gives us 40. Average of that would basically be 43. Equal to 43. All right? So that's the median before. Median after, okay, let's clean that up. Doesn't look cool. The median after would be the same thing, x10 plus x11 over 2. But in this case, what is 10 and 11? It's 30 and 31. 30 plus 31 over 2, which gives us 30.5. So the median after is 30.5. Let's take that and put that up here. So here we see so now with this question, we're going to calculate the range, interquartile range, the standard deviation, coefficient of variation of the age of each of those groups. So what we are now doing is doing some calculations on measures of dispersion or measures of variability. So just to remind you, I guess, of the formulas. So we know range is equal to just the maximum value minus the minimum. The interquartile range we call it IQR, is just the third quartile minus the first quartile. And then the standard deviation on variance, so once we calculate one, we could calculate the other, is the square root of the sum of x squared minus the sum of x all squared, notice that squared is on the outside, divided by n, and the whole thing is divided by n minus 1. So that gives us our sample standard deviation, S. Okay? Maybe we could put that in here. And we need the coefficient of variation. Coefficient of variation now is just simply the ratio. I'm going to just move that here. So coefficient of variation is CV. CV is, if it's population, is sigma over mu, but if it's sample, is S over X bar. All right? So that's a coefficient of variation when we're dealing with a sample. So that's what we will need right here. So since you notice that if we need the interquartile range, we will need to be able to calculate the quartiles. So the question is, how do we calculate quartiles? If you may recall, the median, the calculation for the median, what we did was we took n plus 1 over 2. Now the 2 represented the midpoint because we were considering the median, dividing it into 2. Since we're going to divide into 4, the quartiles are as follows. So Q1 would be x 1 over 4 n plus 1. In other words, the value that's in location, right, 1/4 of n plus 1. Q2, which is the same as the median, would be 2 over 4, which is half n plus 1. So that's a subscript that I'm writing here. Q3 is x 3 over 4, 3/4 n plus 1. So if you think of n plus 1 as is the sample size, so we're going a 3/4 way up. And that brings us to the third quartile. So we have to then calculate those values. So let's see what those would actually be. And we could then do the calculations later, okay? On the next slide. So x 1/4 n plus 1, that's 21. So what's a quarter of 21? 4 goes into 25 times, and there's 1 left, so 5.25. So that's the same as x, 5.25. which basically means that we want to find, if we were to divide this into 4 equal parts. So the first quarter here, 5.25. If you take the 5th value and the 6th value, then this location is a quarter way up between those two. That's why you get 0.25. So we will have to figure out what the distance is between 5 and 6 and take a quarter of that. So to get that value, here's how we usually do it. It would be x5 plus 0.25, a quarter of the difference between x6 and x5. Does that make sense? So that's what we have to do to get the first quartile. We already have the medians, so we don't have to calculate them again. And to get the third quartile, n plus 1, in that case, we're talking about 3/4 of n plus 1, which is 21, 3/4 of 21. Well, it will be 3 5s of 15, but there will be there will be a remainder, so I think we have to go up to 15.75. But let's figure that out. Okay, so if we took 21 times 3, so I'll just do it up here. 21 times 3 is over 4. Well, what is that? That's 5.25, because we know 21 is equal to 5. Divided by 4 is 5.25 times 3, so that's just 15.75. All right? So x 15.75. And to get that, we would take x15, and we have to go 3/4 way up between the 15th and 16th value, plus 0.75, that's 3/4, x16 minus x15. All right? That's how we would do this. Now let us do the actual calculations for each of those. I did not write out all of the ordered set of values, but I'm assuming if you're going to follow with me that you would take the data and order it yourself, and that's fairly simple to do. I don't think I have to necessarily go through and demonstrate all of that. So we will do before over here. For the data before, let's find 5.25. So the 5th value, x5, from the data turns out to be 34, and x6 turns out to be 34. But guess what? There's no distance between that, and so taking a quarter of 0 doesn't give you anything. So Q1 is 34 plus 0.25 of 0, the difference between x6 and x5. So, of course, that is 34. Q1 is 34. Q1. Q3 would be, we need x15. What is x15? x15 is 55. x16 is equal to 56. So there's only a difference of 1 between that. And so Q3 is 55 plus 3/4 of the difference between 55 and 56, which is just 1. In this case is 55.75. So that's the first and third quartiles. We want the interquartile range for before. So IQR before is Q3 minus Q1, which is just 55.75 minus 34, which gives us 21.75. Make sense? So 21.75 is the interquartile range right here. Now we will repeat this for after. Isn't this cool how this shrink that and just move that around? So let's do after. So after, we want x5. And what is x5? x5 for after is 27. x6 is equal to 28. So there's only one difference between those. So of course x5.25, since the sample sizes are the same, we use the same values right here, would be x5 27 plus a quarter of the difference between those two, which is 1. So a quarter of 1 will give us 27.25, right? That would be the first quartile. So Q1 is 27.25. Q3 is x15 plus 0.75, x15 minus x16. So let's figure what that is. Turns out x15 is, the 15th value is 36. Let me just remove this. I don't need to do this twice. It's 36 plus 0.75 times the difference between the 15th and 16th value. X16 happens to be 39. So 39 minus 36 is 3. Alright. So 36, what's 3/4 of 3? That's 3 3s are 9 over 4. 9 over 4 is 2.25. So that'll be 38.25, if I've got this right. So that'll be 38. A little mental math doesn't hurt. Prevents brain atrophy. And so now that I have Q3 and I have Q1, IQR after is 38.25 minus 27.25. Well, the 2 5s cancel out, and then we would have 11 as our interquartile range. So right away you can notice that this 11 is much smaller than the 21.75 right here for before. So the middle 50%, which is the interquartile range, for the age of the new clients is actually smaller than that of the age of the old clients. So this is really cool. Okay, so I'm going to now do the calculations for the standard deviation. And if we have the standard deviation, all we need to do is to square it and we'd have the variance. So we don't have to do anything radically different, radically new. So let us just recall our formulas for standard deviation. We know S is equal to the square root of the sum of x squared minus the sum of x, all squared in the bracket over n, and then this entire thing over n minus 1. Remember, all of this is under the square root sign, okay? Alright, so having done that, let's just recall our values before. Before we have sum of x and sum of x squared is 885. Sum of x squared is equal to 41905. 41905. After, we have sum of x is equal to 641, and the sum of x squared is equal to 21,311. So of course you would be expected to do those calculations, but we actually gave you the values ahead of time. So let's just calculate before. So standard deviation, or let's call it SB. So SB would be, put a nice big square root. It would be the sum of the x squared, so it's 41,905 minus 885 squared divided by 20, and then of course 20 minus 1, which is 19. I didn't have to write the formula all over again since you already have it. Okay, let's just put 20 minus 1, which is 19. And if we do this calculation and we do it right, we will find that we have, this is equal to the square root of 144.41, which gives us 12.02. So I'm assuming that you know how to do your calculations, of course. Let's create some space. It's just so cool. Now we're going to continue with S after. And S after, we have the following. So the sum of the x squareds, if you recall, was 21,311 minus the sum of the x's, which is 641 squared over 20, and the whole thing is divided by 20 minus 1, which gives us, after we do that computation, the square root of 40.37, which is equal to 6.35. So these are our standard deviations right here. Okay, so that's our standard deviations right here. Okay, so now we know SB is 12.02, but if you and then we have SA is 6.35. So what we're going to do now is calculate the coefficient of variation. Still learning to write with this thing. So CV is equal to S over X bar, and so for before and after, let's look at before and after. So CV before would simply be 12.02, but you will recall that our mean was 44.25. 44.25, which gives us a coefficient of variation of 0.2716 when you do that calculation. CVA, which is after, we recall that our mean was 32.05. So we have 6.35, 32.05, and that gives us 0.0. Let's do this properly. It gives us 0.1982. All right? So that's the coefficient of variation for after we have the ad campaign. So you could see, and we could express that as a percentage. This one would be 27.16%, and then this one would be 19.82%. And that allows us to be able to compare those two distributions. And you can see that the coefficient of variation afterwards is actually quite smaller. All right. So now let us do this. Let's just kind of do a summary of what we have for this particular section right here. Just going to move this. Make it a little too smaller, but not too small that you can't see it. And we can now put the following values down. We could say before, after, So now, of course, the real value of statistics is to look at the data and come to some sort of conclusions. So we have this question: using the result in A and B, which is the first two things that we did, comment on the effectiveness of the new advertising campaign. Is it actually working? Well, what was the intent? The objective was to try to get younger clients, because if you get younger clients, then they spend they're able to spend more time with the company. The company can reap greater benefits or greater value from customers that are younger, particularly if they serve them well and keep them as long-term customers. So I would answer yes, and the reason why is because if we look at all of the statistics that we calculated before, we will see that the average age has dropped. We will see also that not only has the average age dropped, we saw the median drop, and the mode also was different, it was smaller. And then we have less variability too. So in fact, not only were we able to reduce the average age, the median age, and so on, but we see that there's actually less variability in the second set of values. That is, the folks after the campaign have less variability in age. So this is all good. I'm sure the company must be happy. Why would the insurance company like to attract younger customers? Well, of course, they want to attract younger customers because younger customers will spend more time with them. All right? So it's about time and time. So more time means more money. Simple. All right? But of course, that's providing that they don't lose those customers because of bad customer service or something of that kind, of that nature. So it's very important for them to make sure that not only that you attract the young customers, but you want to retain them as well. And insurance companies have to do certain things to make sure that that actually happens. Last question. Could Ms. Gail Pooley generalize these sample results to the customer database? Explain briefly. Yes or no is not an acceptable answer. Well, can she generalize? And that's an important point. Well, what allows us to generalize? What allows us to generalize is if indeed we obtain the samples in a manner that is unbiased and that is representative of the population. So remember that we talked about we have a population, and from that population has a mean, it has a standard deviation, we'll generate samples from them. But if that sample is not representative of that population, all of statistics that we calculate, right, median and so on, will not be representative of that population. So we can generalize only if the samples that are taken represents the actual population that the company is interested in. Now, in the first case, it's relatively easy, which is before the campaign. All they have to do is to sample from their own database, all right? But then after, the sample after, if they're able to, if we're not talking about who's out there, but people who've actually decided to be their clients, then again, once they randomly sample from that new database, or the database of new clients, as long as the sample is randomly taken and taken unbiasedly, then you could actually do a generalization of the answers. So I would say the answer is yes, that you can, but given the condition that these samples must actually be appropriate samples. All right? Good. There's one final question, which is, of the two samples that we have, which is the better measure of central tendency, the mean or the median? Now, to answer that question, it depends on whether we have a certain amount of skewness. All right? When a distribution is skewed, the mean is not a very good representation of that. Let's just see what I'm talking about. If the distribution is symmetrical, nice little curve, then sure, mean, median, and mode, they would all be right around the center. But what if we have a distribution like this? What if we have a distribution like this? these extreme values skews the mean. What it tends to do is that if the median is here, it pulls up the mean, that's median, it pulls up the mean higher, it pulls up the average. So in this case, the mean would tend to be higher than the median. All right? If we have this situation where you have a lot of small values in there, not a lot of small values, but some small values in there, some extreme values, then say if the median was here, what happens is that those values will pull down the mean. They'll pull it down. That's the median. All right? And so in this case, the mean would be smaller than the median. So if we go back to our values, let's take a look at the difference between the means and the medians. For before, the mean was 44.25. The median was 43. After, the mean was 32.05 and the median was 30.05. I think those are pretty close. So we're talking about before, mean and median was 44 versus 43, 44.25, sorry, versus 43. These things are, for all intents and purposes, the same. Afterwards, we are looking at 32.05 and 30.05. Recognizing that we're dealing with samples here, and we expect some variation. We don't expect to get the exact values in the population. I would say those are also pretty close. So given that the means and the medians are pretty close, to me it really doesn't matter which one you use in this case. Those distributions are likely closer to being symmetrical, which is this one right here, than one of those two over here, which is that one and that one. I don't think that distribution looks like the skewed distributions here. If we call this A, B, and C, it doesn't look like B and C. It looks more like A. Those values are pretty close. So I would say the median or the mean, either of them can be used because I believe that the distributions are pretty close. Okay? So they're not very significant. We could use either of them. That brings us to the end of our example on descriptive statistics. So we hope you found that useful, and the job now is to actually do these exercises on your own to ensure that you totally understand what's happening in those two segments of the course. Thank you.